It's a new era of pioneers, star sailors, thinkers, and adventurers.
4 brave explorers ready to ride the most powerful rocket NASA has ever launched. And liftoff!
The race to build the first permanent base on the moon has already started. 2 countries are targeting the same region. Hardware is under contract. The first missions are launching before the end of 2026, and whoever gets there first gains access to the resources that could shape every mission beyond the moon for decades. Most people are not watching this closely enough, and it is considerably further along than the coverage suggests. Let's put this in context, because the framing matters. For most of the past decade, we have talked about Artemis as a return mission. America is going back to the moon. Flags and footprints, round 2. That framing made sense when the program was about proving the hardware. Artemis 1 proved the SLS and Orion architecture could fly. Artemis 2 sent 4 astronauts on a crewed lunar flyby in April 2026, the first humans to travel toward the moon in 53 years, returning home safely 9 days and 1 hour later. Both of those things matter, and we should not understate them, but they are the opening act. The Moon Base Initiative, announced at NASA's Ignition event on March 24, 2026, with a $20 billion commitment over 7 years, is a completely different category of ambition. The goal is sustained human presence near the lunar South Pole, built through a phased plan that begins with robotic systems and scales toward continuous crewed operations. Phase 1 is already underway, with Moonbase 1, the first dedicated surface mission, targeting launch before the end of 2026. Phase 2, beginning in 2029, introduces semi-permanent infrastructure, nuclear power, pressurized rovers, and early habitation supporting semi-annual crew rotations. Phase 3 targets continuous crewed presence and 38 tons of annual cargo resupply to keep the base running indefinitely. We are watching the transition from mission planning to operational architecture. Those are genuinely different things. The South Pole is where Moonbase is going, and we need to understand why, because the answer drives every decision downstream. The reason comes down to resources. Most of the lunar surface is hostile to long-term operations. Equatorial regions swing between weeks of brutal sunlight and weeks of complete darkness, making consistent power and thermal stability nearly impossible. The South Pole solves that problem. Certain ridgelines near the pole receive near-continuous solar illumination, which means viable power generation. And sitting in permanently shadowed craters a short distance away is water ice that has been accumulating for billions of years, preserved by temperatures as low as -334 degrees Fahrenheit that no sunlight has ever disrupted. That ice is why we care, and it is worth being specific about what it actually represents. Processed water ice becomes drinking water and breathable oxygen. Split into hydrogen and oxygen through electrolysis, it becomes rocket propellant. We are looking at the raw materials for life support and transportation, sitting in craters that humans can reach and eventually extract. The program that builds the infrastructure to access those resources gains a refueling depot that changes the economics of every mission beyond the moon. That is the strategic prize, and it is why both NASA and China are targeting the same small patch of lunar real estate. NASA's Viper rover is conducting the first detailed resource mapping mission of the region, pinpointing exactly where ice deposits are concentrated before Phase 1 construction commits to specific sites. Shackleton Crater, more than twice as deep as the Grand Canyon and sitting at the edge of near-continuous sunlight, is a leading candidate. The region also sits near the South Pole Aitken Basin, the largest and oldest known impact crater in the solar system, whose samples could tell us things about the early solar system that no other accessible location can match. The South Pole is worth the engineering difficulty it presents. We need to talk about mobility, because it is the capability that determines how much of the South Pole we can actually use. Most people picture the Apollo 17 buggy when they hear lunar rover, 2 seats, open frame, limited range, left on the surface. NASA's next-generation systems are a different category entirely. In May 2026, NASA awarded contracts to Astrolab and Lunar Outpost to build 2 crewed lunar terrain vehicles, with Blue Origin's Blue Moon lander delivering both to the surface before the first Artemis astronauts arrive. These machines are built for extended traverses, cargo transport, and surface preparation well beyond anything Apollo attempted. Phase 2 adds a pressurized rover from JAXA, Japan's space agency, allowing astronauts to travel significant distances without spacesuits and dramatically expanding the operational range of each crew rotation. This is where the picture gets bigger. NASA is also deploying Moonfall, a JPL-managed mission sending 4 propulsive drone hoppers to the lunar South Pole in 2028. Firefly Aerospace's Elytra spacecraft will transport and deploy them mid-descent, after which each drone lands independently and spends a single lunar day capturing high-resolution imagery with up to 10 cameras across terrain that no rover can safely enter. After their final flights, their survive-the-night payloads continue operating for months, marking the perimeter of the future base site. Permanently shadowed craters hold the ice. Drones are how we map what is inside them before committing crews. Sustained operations only become viable once we can move people, cargo, and reconnaissance reliably across terrain no human has ever stood on. The mobility program is how we earn that confidence before crews depend on it. If we strip the engineering away and look at this honestly, Moonbase is a supply chain problem. The habitats, the fission reactors, the science outposts, all of it is downstream of one challenge: getting enough cargo to the surface, reliably enough and cheaply enough to sustain continuous operations year after year. Phase 3 calls for 38 tons of annual cargo delivery to keep the base running. Reaching that cadence requires reusable heavy-lift landers operating closer to a commercial freight schedule than a traditional NASA mission timeline. The Commercial Lunar Payload Services Program, which already delivered scientific payloads through Firefly Aerospace's Blue Origin lander in early 2025, provides the initial commercial pipeline. Heavier cargo variants are under development for Phase 2 and Phase 3. This is why the partnership structure matters as an engineering requirement. European Space Agency, JAXA, and commercial partners are contributing hardware at every layer. JAXA's pressurized rover, communications relay satellites designed to provide at least 500 megabits per second of bandwidth between the Moon and Earth, nuclear power components, and cargo lander capacity at multiple weight classes. Sustaining the throughput Moonbase requires over the next decade exceeds what any single agency can deliver. Without that network of partners, this does not happen. That is worth sitting with. The lunar night is the engineering problem that could shut down this entire program if it goes unsolved. And we should be honest about exactly why. Away from the South Pole ridgelines that receive extended sunlight, temperatures swing from over 130 degrees Fahrenheit in direct sun to minus 334 degrees Fahrenheit in permanent shadow. Electronics fail, batteries discharge completely, mechanical systems seize. Hardware built for Earth winters does not survive a single lunar night. If NASA cannot solve this, the base goes dark every 2 weeks. And a base that goes dark every 2 weeks is not a base. That is the problem. Here is how the program addresses it. Phase 1 includes radioisotope heater unit demonstrations using the decay heat of plutonium-238 to keep electronics and mechanical systems functional through cold periods. Phase 2 introduces nuclear fission surface power with a 20-kilowatt reactor ready by 2028 that is scalable to 100 kilowatts or more, capable of delivering steady energy through lunar nights, through dust storms that coat solar panels, and inside the permanently shadowed regions where ice extraction would eventually take place. A fission reactor produces power regardless of whether the sun is up. That is exactly the property this environment demands. The thermal challenge extends to every subsystem: habitation modules, life support, communications, and the rovers themselves. Phase 1's rapid series of robotic missions exists specifically to gather operational data under real conditions before crews depend on it. If we want to understand why NASA is investing so heavily in all of this, we have to look beyond the Moon. The South Pole is where we earn the right to attempt Mars. Every system we prove there removes an unknown from the Mars equation, and Mars carries a lot of unknowns. The journey takes 7 months each way, and windows open only once every 26 months. Once a crew departs, there is no abort and no resupply on short notice. Anything that fails on the Martian surface has to be fixed with whatever was brought along or built locally. Landing large cargo payloads is a severe problem because Mars has enough atmosphere to generate dangerous heating during entry, but too little to slow very large vehicles efficiently. This is why the Moon matters so much. Fission power proven through a lunar night is the same architecture Mars surface operations require. Pressurized rovers operated across lunar terrain to develop the failure mode knowledge needed for Mars traverses. Ice extraction techniques proven at the South Pole build the foundation for producing methane and oxygen propellant on Mars, which is the plan for fueling return vehicles without shipping propellant from Earth. Every system that succeeds at the South Pole reduces the risk margin on the first crewed Mars mission, which NASA's current architecture targets for the late 2030s. The Moon is the test bed, and the test bed now has named contractors, funded phases, and launch dates behind it. Let's sit with what has actually changed, because it is easy to miss beneath the announcements. NASA is now talking about the Moon in operational language: cargo tonnage per year, crew rotation schedules, power redundancy, annual resupply cadence, and contract awards with delivery dates attached. These are the conversations you have when you are planning an outpost. Administrator Isaacman said it directly on May 26th. The Moon base will be America's and humanity's first outpost on another celestial world. Not a visit, an outpost. He has also been explicit about the competition. China's parallel program is targeting the same South Pole region, on a timeline that converges with NASA's by the end of the decade. The decisions being made right now about which systems to fund and how fast to move will determine whether the United States builds the first permanent outpost on the Moon or arrives second to a region that can support only a limited number of programs at once. Apollo proved we could reach the Moon. Moonbase is the plan to stay there. Moonbase 1 is targeting launch before the end of 2026. Viper is heading to the surface. Astrolab and Lunar Outpost are building the rovers. JPL is building the drones. This is not a future program. It is a current operation, past the point of announcements and into the phase of contracts, hardware, and launches. If the phased plan holds, permanent infrastructure will exist near the lunar South Pole before this decade ends, designed to grow and to last beyond any single administration or any single mission. The question is whether we are paying close enough attention to what is being built right now.